All right, for week 5, day 1, we've got some number theory and group theory mixed in here. Consider the Diophantine equation, 7x minus 5y equals 1. You were told in algebra you can't solve an equation with 2 unknowns, but that's not true. You can do that, and the way that we would do it is we would trial and error, try to find a value that would work for both of those. So if I put in a 1, that's not going to work. Put in a 2, 14. Is that going to work? No. Put in a 3. 21 minus what? 20. So you could go 3, right? And 4. You just try, you go until you can figure it out. Now, it says find the general solution for this. So what we're going to do is we're going to say x is going to be 3, and then, we're going to have some multiples of that. So we could go plus 5n, and y is going to be 4 plus 7n. Where n is an element of the integers. Okay, so think about this. Let's say n was 1. Okay, so you get 8 and 11. Does that work? 56. Let's see, where's that? Did I do that right? If this is 8. Okay, 1 is going to be 8, and then this will be 11. 7 times 8 is 56, and 5 times 11 is 56, minus 55. Yeah, that works. So you could do that. So I think that's your general solution, 3 plus 5n. Yeah, so you're going to take your solution plus this coefficient times n. Then for the y, it's going to be the solution that you found plus that times n. And you can see where the points would be 1, 2, 3. Hence, find the solution. Oh, there's your favorite word in IB. Hence, find the solution with the minimum positive value of x times y. Is 3 times 4 the minimum value? What would work? Subtract 5 and you're going to get -2, and then subtract 7, you get -3, and you're going to get 6. So they're just trying to zip you there. By the way, could you do this? Better try the other one. Do it another. If we subtracted another 5, you'd get -7 times, oh, that's not going to work, is it? Yeah. Nah, we're done. All right, then it says C, find the solution satisfying xy equal to 2014. So we just take that where we said x was 3 plus 5n, right? And then we have 4 plus 7n. And that's going to be equal to 2014. Now, I tried this with their minimum value. I don't know if it'll work with this one, if it'll be the same. Here's what we'll do. Let's try 2 here. You guys solve this one on this half of the room. And then the other side, do -2 plus 3n times -3 plus 7n, 2014. This is a 5 here. I don't think it would matter, but I want to double check. So now what we did is we took these two, subbing in. It doesn't matter which one you pick, just be consistent. Notice that this is the term, this is one term higher than this one. So this n is going to be one term higher than this is. Either way will be fine. X is equal to negative 2 plus 5 times 8. And y will be equal to negative 3 plus 7 times 8. So 40 minus 2 is 38, and 56 minus 3 is 53. These are the values for x and y. Notice what happens if you were to use this one here. You would have x is equal to 3 plus 5 times 7. 35 and 3 is 38. And y is equal to 4 plus 7 times 7. 49 and 3 is 53. What do you notice? Same solutions. Go to the next one, 2. This one is even better. It says, consider the recurrence relation hn plus 1 equals 2hn plus 1. Find h2, h3, h4. Let's do it. H of n plus 1 is 2 times the previous. Well, they're saying h1 is 1, so this couldn't be simpler. 2 plus 1 is 3. So this is going to be h of 2. H of 3 is going to be 2 times 3 plus 1, which is 7. H of 4, 2 times 7 plus 1 is 15. Those are the answers you're looking for part A. And then it says conjecture an h of n that doesn't have the recursion formula in it. So h of n, not 2, h of n, what pattern do you see with these? Are they increasing by the same amount each time? By the way, the first one is 1. No, this is 2, 4, 8. What does that make you think of? There's like an exponent thing going on here. So I'm going to remind you what, if you were to look at 2, 4, 8, 16, is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. What do you notice about this pattern? Yeah, so this is 2 to the n, what? Minus 1, yeah. And how many points is this one worth? 1. So this is, you don't have to show anything or explain anything. Now, this is the cool part. Prove by math induction, your favorite, that your formula is valid. So what you're going to do is you're going to check for n equal to 1. And n equal to 1, all you're going to do is h of 1 should be equal to 1. True for n equal to 1. What else should we check? N equal to k. So this is our assumption statement, and h of k is equal to 2 to the k minus 1. Now here's where the fun begins. We know for n equal to k plus 1 that the formula is the recursion formula h of n plus, or h of k plus 1 is equal to 2 times h of k plus 1. I'm going to double check that. Yes. How can we use this to our advantage? Yeah.
So if you put it in, plug in, say when you put h of k up there, and then you get it for 2.
H of k plus 1 is going to be 2 of 2 to the k plus 1. Do you like this? I like this a lot. So this is 2 times 2 to the k plus 2. I had a little error in here. It's not big. It's a little tiny error. This was supposed to be 2 to the k what? Minus 1. So this is going to be minus 2 plus 1. Right? Okay, so then This is 2 to the k times 2 to the 1 minus 1, which is the same as 2 to the k what? Plus 1. That's what h of k plus 1, and this is actually true for n equal to k plus 1. Because that's just 2 to the k plus 1. Isn't that neat? They use that recursion formula to help generate that n h of k plus 1. Then you say, therefore, since true for n equal to 1, are we doing strong or weak? If it's strong, we have to go 1 dot 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 to k. It's the only thing we have to do different. Doesn't say strong, so then we go and we go weak. Yeah. N equal to k plus 1, then true for, and this is the part you need to include, n greater than or equal to what? What was our first term? 1, so by math induction. And don't spell it D-U-C-K.